Hey, good afternoon. And Gopi, and I work for Mojo Networks, and we have come from India. And just in case you don't know, it's a 20-hour flight, and not to mention of the layover and the jet lag, where you're a zombie in the morning and you're wide awake at the night, right? So it's some experience that all of us should go through. But I think over the last 3 days, I think it's been really worth it. And it's good. There have been a lot of good sessions. I've learned a lot. And hopefully you'll also enjoy this session. And really, it was good to meet some of the old friends and also trying to make some new friends, right? So that's a bit of introduction about myself. And what I'm going to speak today is Wi-Fi issues in the wild, a view from the cloud. So for those of you who are familiar with data mining, right, at some point of time or other, you may have done that yourself or come across that. I think this is a very enjoyable exercise, but I'll tell you, it's also it can be a painful exercise. We need to do a lot of iterations. We may or not find anything. It's like treasure hunt, right? But if we find something interesting, then that's the aha moment, right? So hopefully we have found something in our analysis, and that's what I'm here to share about. And then let's see how this goes. Okay, that's the quick background. And the first thing I would like to mention here is that Mojo Networks, we make Wi-Fi access points, and we have a slightly different architecture. So it's a cloud-based architecture. And what I'm going to tell you today is that just because of the cloud architecture we have been able to mine so much data and do things like cross-customer data mining and analysis and get some insights about how real-life Wi-Fi deployments are looking like today. Okay, so we have a centralized manager which sits in the cloud, and basically we have a instance, cloud instance as we speak, which is managing 100,000 live access points today. Okay, that should give you an idea of the scale at which we are operating. So we have the data plane, which actually can be a local breakout, or we have an ability to tunnel it through what we call as a multi-service platform. But the interesting thing is about the control plane. So the moment we are a true cloud vendor, there is no controller in the picture. So if the controller is not there, how are we going to actually make sure that the RRM, the auto transmit power, and those kind of decisions are made in the WLAN, right? That's where the distributed control plane comes into picture. And our engineering team has spent a lot of time to actually perfect this almost like art and science, right? Like this is one of the challenging problems we had to solve. And we are proud to say that, yes, this can work, right? So that's about the control plane. And the key point here is that it's robust, that it works even when there is no connectivity to the cloud. I think that's something which is hard to achieve, but we have been able to achieve that. So these are the components that are there in any typical WLAN, right? So yes, it's a cloud-based and slightly different. But what I'm going to talk slightly more today is, in addition to these three planes, the data plane, control plane, and the management plane, we also have the cognitive plane. And this is something which runs as a fabric throughout the network and has components at the access point, the backend server, the cloud, and then brings some kind of intelligence into the system, right? And it has a big data component where we store certain key parameters related to the system or client health. And we also have smart edge access points which are deployed at the premises, and they have a lot of processing power, and they also implement some techniques or algorithms to actually identify certain failures. So our philosophy has been, we need to enable the users to find the needle in the haystack, right? We don't believe in throwing a lot of data at the user and then go figure out. I mean, that's not been our strategy. We always have tried to give processed information and give as much insights to the user as possible, right? So what are the kind of failures that we are going to focus? Am I audible? Okay, great. So we are going to focus on two key types of failures. One, what we call as the connectivity failures. We all know when a Wi-Fi client connects to the network, it goes through multiple stages of connection. It's the authentication, it's probes, then authenticates, associates, then maybe there is a radius authentication, and then it has to get address from the network, and then only it is able to transfer data, right? So there can be some failures in this stage, and that is what we call as connectivity failures. And we use the term called client journey, where we trace this whole process as a client connects to the network. And this is very much in philosophy of Mojo Packets, which is a tool we launched in 2013. And it has been well supported and received by this community. Thank you all for that. And if you recall, the philosophy behind Mojo Packets is also helping the user identify failures quickly and then do more deeper analysis around those failures, right? So that we are continuing on that journey. And the other point I would like to mention here is that we provide a lot of useful insights with respect to clients when they connect to the network. And what we are calling in your system as client event logs, that is one of the key things we are using in this presentation today. And it has been in our system for the last couple of years, I would say. I think I could not help but notice that one of the vendors also launched it yesterday at WLPC, which is good. But we have been having in our system for quite some time. But in the same spirit, we would also like to launch something else in the WLPC today. And this is what we call as user application experience. And what we mean by this is that a lot of times we talk about connectivity issues, performance issues. They are important, but finally what matters to a Wi-Fi user is whether their applications are working or not. And that is something we believe is the kind of holy grail, and we are taking some steps towards achieving that. And I'm happy to announce that this specific feature is something out there, and it's actually beta and close to production, and we would definitely love some feedback on this. Basically, we are trying to detect whether specific applications are working or not. If there is a failure, why is it failing, and so on. So that's what we are calling as user application monitoring. So now coming back to the performance aspect of Wi-Fi. So what we are looking at here is that there can be several reasons why a client can experience poor performance. It may have connected properly, but still there may be some issues in terms of accessing the web. It may be very slow and so on. That's why we say that the Wi-Fi sucks, right? So we want to understand why this can be happening, and we store a lot of useful parameters about the client, the traffic flows in our system. And the important point to note here is that we have anomaly detection based on baselining technique, and we store various parameters, their moving averages, and see how they kind of how they are behaving in a specific network. We all know that a lot of these parameters like retry rate, right, or the data rate of a client, right? There's nothing which is right or wrong, right? So it depends on the deployment, and then that is why we dynamically find what is the baseline in the specific deployment and identify anomalies with respect to that baseline. So this is a performance failure, which I'm going to talk about. Okay, so now I'll kind of begin the failure analysis by showing a glimpse of the data that we have used, because data is very important. And we look at the connectivity failures in more depth, then the performance failures, and finally, we'll see what are the key takeaways from this presentation. So the reference data. So we have anonymized data from a subset of our production cloud, and we have looked at 237,000 plus clients and more than 31 million associations, and the clients are using about 400 plus applications, and we have collected the data for about 1 week. And for the purpose of this session, we have looked at data mostly from North America and then Europe, and we have not considered data from the Indian geography because a lot of things may be specific there. And the reason why we are looking at data for 1 week is that we see that can give a good statistical, that can give us good statistical idea about the performance of these failures. And we have looked at multiple weeks data, and we see that there is a lot of similarity. So we are restricting the analysis to 1 week data. The other interesting thing I want to point out here is that we've been able to get data from multiple verticals. One is the enterprise vertical, then the education vertical, the manufacturing and automobile sector, and also retail and hospitality. So the important point to note here is that one of the perceptions in the industry is that cloud is only applicable or relevant in retail and hospitality industry, maybe in retail industry where there is not too much of load. But we can see that we have been able to deploy we have cloud deployments across all verticals, including enterprise and education. And we definitely believe that cloud architecture works across all verticals, and we don't need to restrict it only to certain specific verticals. Right? So quickly, let us look at the apps that have been that are being used in our deployment. We see that clearly the Google apps dominate. Right? I think that's something that's not that's surprising because everyone uses it today. And as I mentioned, we have got more than 400 plus apps that we have seen that the clients are using. So we've been able to identify all this because we got a deep packet inspection engine, and we run a lot of algorithms at the back end to determine and come up with some of these statistics. So now looking at the connectivity failures and the latencies. So this is something we know, right? Even in this conference, we have heard a lot of talks, and then we've seen a lot of tweets where people say that, yes, Wi-Fi is not working fine. And many times, yes, it is true, especially with 2.4 gigahertz. We do know that there can be some issues, right? But then we want to see when people say Wi-Fi is not working fine, can we actually analyze, go one level deeper, peel the onion, so to say, and then see why it is not working fine. So that's the exercise we have actually taken. And to begin with, the connectivity failures, right? So we see that there are a lot of stages that a client goes through before it is able to access the network. So the association stage is there. There can be some failures at the association stage. Then there can be some failures at the authentication stage, right? Then there can be some failures at the network level as well. So example of authentication failure is that the radius authentication failed, or the radius server is not reachable, right? It can fail. It has nothing to do with Wi-Fi, but still that leads to a very poor user experience, right? Similarly, on the network side, a DHCP address may not be available because maybe the DHCP server has run out of addresses. So, but still the client will fail. It has nothing to do with Wi-Fi again, right? So we've instrumented our access point with a lot of triggers in the, to tap the client state machine, and then using that we are able to identify where the client exactly is failing. And since we are in the data path, this is the ultimate truth, and we have information about that. Okay, so what we saw is that about 6% of the connections fail in a well configured and operational network. So again, this is something which is not alarming, but at the same time, right, we are seeing that there are some connectivity failures that are happening in the network, and we need to, it merits some analysis, right? So this 6% connection failure corresponds to about 5% of the clients, because the client may fail multiple times because of the periodic nature of the Wi-Fi connection and so on. But if you see, we have got about more than 3,000 connections that are happening in our network per minute. So 5% of this is roughly about 120 to 150 failures. Of course, they are not happening in one place. As I said, we are analyzed more than 31 million associations, and they are happening in a distributed way, but still it is a significant number which we need to understand better, right? So what we found intriguing is the fact that, yes, even in a in a network that is operating normally, why are we seeing these connectivity issues? Because if the user is able to actually configure the password properly, most likely radius in an enterprise network or in a guest network like PSK, right? There should be no connectivity failures. I mean, you just got to connect, but still we are seeing these failures, right? So why? So that's the question we are trying to answer here. So we kind of went one more level deeper and saw how these kind of, what is the distribution of these failures, right? Between association, authentication, and network. So what we are seeing here is that more than 50% of the connection failures are due to wire side issues. So that at least confirmed to us that, yes, there is a element that is beyond Wi-Fi, which is playing a role here, and we want to understand this further, right? And the interesting thing to notice here is that the association failures, which are very, very specific to Wi-Fi, they are very limited, right? We see hardly 1 or 2% of that, and then that's not significant at all. So we are seeing issues with respect to authentication layer and the network layer. Now let us go one more level, peel the next level, next layer of onion, so to say, right? So what we are seeing is that there are about 25% failures that are due to DHCP issues, right? Then other 25 or 27% roughly are due to DNS failures. We see that DNS is a very it's like a stateless protocol, right? Like it's a request that goes and the response has to come by, right? A lot of times we see that the DNS failure happens, but then if the DNS failure happens, it does not matter. It's still a poor user experience, and it's like perceived to be very bad. So that explains that more than 50% of the failures are due to the network layer, which has nothing to do with Wi-Fi. Now let us focus on the Wi-Fi failures and see if there is something interesting, right? So we see that there are about 19% failures which are related to incorrect PSK, right? So this is again something interesting because PSK is something which is not typically used in enterprise for enterprise access. It is mostly used in guest access, be it in the retail or hospitality industry, or in enterprise to provide guest access, right? So we believe that this may be due to things like the BYOD devices that users are getting, or maybe some guests who are coming, who are putting wrong PSK passwords and so on. That is what we think is happening here. And the other interesting thing is that we are noticing there are about 13% EPOL errors. This is something strange because EPOL is a very simple protocol and it has to succeed, right? And we know that periodically rekeying and those kind of things happen in a Wi-Fi network. And we expect that if it succeeds once, it has to succeed 100 times and 1,000 times. But we are seeing that there is some element of probability here, and EPOL failures are seen seen with the clients. And this may be because some packets are probably getting dropped, or maybe there is some bug in the implementation which needs multiple attempts to kind of succeed. But we do see these kind of failures as well. And the good thing about these failures is that they're transient in nature. Most of the times, if there's a EPOL failure, it auto-corrects itself. But then user may notice it in the form of a delay in the connection and so on, right? That way it is still relevant and it merits some discussion. That's the reason why I'm having here. So maybe one final point on this. So we do see there are some captive portal related failures as well, but knowing that there are some strong opinions in this room on captive portal, I'm not going to talk about that. Anyway, that's a very small, less than 1%, so we can just ignore that, right? So now let me ask you a simple question, right? So this is a trick question, mind you. How many of you think that the connectivity issues are similar in both the bands, 2.4 and 5 gigahertz bands? By show of hands. Yeah, so we see hardly 2-3 people, right? Maybe some people know the answer, but they didn't raise the hand, but then we'll give it the benefit of doubt. So this is an interesting question, right? If you look at the answer here, not many people at least raise their hands. So when I ask this question to different people, I've got different answers. Some people think, yes, maybe because 2.4 gigahertz is crowded, we may see more connectivity issues there. Some people think, no, 5 gigahertz is more clean, so maybe there is a higher percentage of connectivity errors. But whatever data is kind of revealing is that the connectivity issues, right, are independent of the band. Like we see pretty much they are similar, and I think there is an explanation for that. And the explanation is exactly what we discussed a couple of minutes back. A large percentage of failures, majority of these failures are due to wired issues, and wired issues are independent of the band. Right? I think that is what it is seeing, and as I said, we can potentially get some good insights where we look at the data, and this is, I think, something which is interesting the data is actually showing. Okay, so now let us look at this data from different verticals perspective. So as I mentioned, we have looked at enterprise, manufacturing, education, and retail and hospitality data, right? So what this graph is actually indicating is the relative distribution of the failures with respect to these verticals. We are trying to see whether all these failures are actually roughly same across these verticals, or they are different. That's why the y-axis, if you see, is 100% is normalized. And one interesting observation we can take away from this is that the DHCP and DNS errors, they predominate in the retail and hospitality industry, right? And I think this is something, in hindsight, it is very obvious, because that is the vertical, the nature of the industry is that there are a lot of guest users. You have a kind of a flux of transient users, and we may run out of IP addresses very easily in such scenarios. So I think one of the key takeaways here is that especially customers from the retail and hospitality industry have to give special attention to these DHCP addresses and make sure that they don't lead to poor user experience, because our data is clearly indicating that yes, that is what is the predominant cause for poor user experience in such verticals. So now switching to successful connections. So far we talked about failures. Now let us switch to successful connections, because there are some good insights we can see from there as well. So what we are seeing here is that the AAA latency, right? I know, I think VP from 7 Signals mentioned about this in his good talk yesterday. So the AAA latency is really large. I mean, it dominates the whole connection process, and that is what our data is clearly indicating. So we're seeing that more than 62% of customers have their baseline, I mean, only 62% customers have their baseline latency below 500 milliseconds. And remember, 500 milliseconds is large in the Wi-Fi world, right? So that's something interesting, and hold on to this thought. We'll come back to AAA latency again. And similarly, DHCP latency, if you see, I think DHCP is a very lightweight protocol, and compared to AAA, we are seeing that most of the organizations have the DHCP latency below 100 milliseconds. I think that's good news, and we will come back to more analysis with respect to these latencies later. So now let's quickly move on to the performance failures and latencies, okay? So again, from a design philosophy or design perspective, we have taken a completely different stance here. Our EP can also collect tons of metrics, right? I think we also collect a lot of metrics. But then what we have realized is that when it comes to characterizing the health of a specific client, all we need are a few parameters, handful of parameters, and we have currently nailed down to only 4 parameters. One is the RSSI. I mean, is it operating at low RSSI? I think there was a good talk previously entirely dedicated to RSI. That's very relevant. Then the low data rate is what is the data rate at which the client is operating? Then what is its retry percentage, right? And whether a client is sticky or not. And sticky client is basically a client which is connecting to a farther access point, even though nearby access point is actually available for connection. And we've used some rough guidelines in our analysis. Basically, low data rate means a client is connecting less than 20 Mbps, and low RSSI means it is connecting less than minus 70 dBm. And I think since most of the deployments are planned with kind of parameters like this, I think our analysis is closer to reality, because this is what people mostly use in practice, right? So now looking at the performance failures, we clearly see that there are 19% of the clients that are affected due to performance issues. And now contrast this with 5% of the clients that are affected due to connectivity. So I think this again is something which is very much explainable. We all know that performance problems are more rampant than connectivity issues, right? So our data is also confirming that it's about roughly 4x the kind of this is the ratio we are seeing between performance issues and connectivity issues. And we clearly see that the low data rate factor is what is the dominant factor. So what we mean by this is that most of the clients that have faced performance issues they were having lower data rate. Again, this is something which is interesting. We all know that data rate plays a very critical role in the performance of whole Wi-Fi network, not just specific client, but the entire BSS. If a specific client or a group of clients are having lower RSSI, then the entire BSS throughput is going to come down, right? That is something which is well known, and we need to make sure that we kind of take care of the low data rate parameter when deploying networks, right? So now let us see if there are any useful insights when we kind of analyze this across the bands, 2.4 and 5 gigahertz bands. So again, we clearly see that the 2.4 gigahertz band is more affected, which is very clear. And the important point to note here is that there are about 3 times the number of clients in 2.4 gigahertz which have lower RSSI is 3 times that of 5 gigahertz, right? And what could be the reason for this? Again, this is something which is explainable, because we know that there are clients who actually prefer 2.4 gigahertz when they are on the fringes, right? So yesterday we had a lot of good discussion in terms of the transmit power of APs, then the cell size and so on. So what we are seeing in our data is that probably there are some deployments where the 2.4 gigahertz is dominant compared to 5 gigahertz, and that is why clients are actually connecting to 2.4 gigahertz, right? So this is something which needs some fine tuning, and at least that's a good insight we've been able to derive out of this analysis. And with respect to verticals, we see that yes, they're pretty much same, and there's nothing interesting here. Let me just quickly flip this slide. And DNS latency is mostly around, I think, 3/4 of the time it's less than 100 milliseconds if the connection succeeds, right? Then the WAN latency is again less than 100 milliseconds. We know that this has nothing to do with Wi-Fi. It depends where exactly the access point is deployed on the WAN link and so on. But this is just another metric just to keep in mind, right? So here is something interesting, right? So we have all this data, right? I mean, what can we do? We have derived some insights, which is good, but we believe that there is more power to this. One of the things that we can do is compare and contrast how different verticals are behaving, how different customers are behaving with respect to these metrics, right? So what we are seeing here is that if we look at the baseline median, the latency, baseline latency median for some of these latencies, right? We see that there's some pattern that is there clearly. Clearly, across all the verticals, the AAA latency is dominating, which is expected, right? So how can we use this information? So one, definitely every organization or customer or vertical can actually look at this and baseline how they are behaving with respect to this benchmark. Right? So that's something we can do as a community, as a industry. If we start publishing these things, each organization can look at this and see where they are with respect to the median. Are they in the top 50% or are they at the bottom 50%? If they're at the bottom 50%, then we can see why it is so and what can be done to improve this. This is what we call as customer benchmarking or vertical benchmarking. The other interesting thing that we can do from these results is that see what is the first order parameter that can be actually tuned to get the maximum bang for the buck in terms of improving network performance. It is very clear that it is the AAA or the radius latency that we need to worried about, and things like fast roaming, right, be it OKC or some of the other 11-hour based roaming, they will definitely help here, right? So they are in the right direction. And also I learned from Dr. Srikanth, who's been one of our good friends, that there's been a lot of activity in the standards, IEEE standards segment to improve this connection latency, and we can clearly see that these are all really making sense. So finally, if you look at the data and validate some of the activities that are going across the standards and the industry, right, like we'll be able to do a better job in terms of having having better Wi-Fi experience and make sure that the Wi-Fi users are happy. I think that's one of the key things that I'm hoping to kind of convey today. And here are some of the key takeaways that I would like to leave you with. And I think you can read it for yourselves. And if there are any questions, I'll be happy to take them.
Thank you very much. That was
thank you.
Amazing amount of data. Thank you, Gopi.